Welcome to the world of dimensionality reduction. In this video, we'll explore how to transform high-dimensional data using two powerful techniques: principal component analysis, often called PCA, and t-distributed stochastic neighbor embedding, known as t-SNE. So, what exactly is dimensionality reduction? It's the process of reducing the number of variables in a dataset while still keeping the important information intact. Think of it as transforming a complex puzzle into a simpler one. This transformation takes high-dimensional data and represents it in a lower-dimensional form. It helps us with visualization, making it easier to understand the data. It also improves computational efficiency, allowing our algorithms to run faster. Dimensionality reduction removes noise, focusing on the most important aspects of the data. It is essential for handling the curse of dimensionality in machine learning, which occurs when data becomes sparse and difficult to analyze in high-dimensional spaces. Why should we care about dimensionality reduction? First, it makes data visualization possible. It enables us to visualize high-dimensional data in 2 or 3 dimensions, making patterns and clusters much easier to see. Second, it increases computational efficiency. By reducing the number of variables, we reduce computational complexity and memory requirements, so algorithms run faster on lower-dimensional data. Third, it helps with noise reduction. It eliminates redundant features and noise, focusing on the most important patterns, thereby improving the performance of our models. Finally, it mitigates the curse of dimensionality, where data becomes sparse in high dimensions, making distance metrics less meaningful. Dimensionality reduction helps to make the data more dense and manageable. Let's dive into principal component analysis, or PCA. It's a linear dimensionality reduction technique that identifies the directions, also known as principal components, of maximum variance in the data. PCA transforms data into a new coordinate system where the axes are orthogonal, meaning they are at right angles to each other. The first principal component captures the most variance, followed by the second, third, and so on. PCA is based on the eigenvalue decomposition of the covariance matrix, a mathematical process that helps identify these principal components. While PCA preserves the global structure of the data, it may not always maintain the local relationships. Now let's explore how PCA works step by step. First, standardize the data. This involves ensuring that the data has a zero mean and unit variance, which means centering the data around zero and scaling it. Second, compute the covariance matrix. The covariance matrix describes how much the variables in the dataset vary from each other. Third, calculate eigenvectors and eigenvalues. Eigenvectors represent the directions or principal components, and eigenvalues represent the magnitude of the variance captured by each eigenvector. Fourth, sort eigenvectors by eigenvalues in descending order. This helps prioritize the components that capture the most variance. Fifth, select the top k eigenvectors to form a projection matrix. The k value determines the number of dimensions you want to reduce to. Sixth, transform the original data using the projection matrix to obtain the reduced dimensional representation. Here is a Python implementation of PCA using scikit-learn. First, the data is standardized using standard scalar. Then, PCA is applied using the PCA function, reducing the data to 2 components. Finally, the explained variance ratio is obtained to understand the variance captured by each component. Explained variance is a crucial concept in PCA that helps determine how many principal components to keep in your reduced dataset. Each principal component explains a certain percentage of the total variance in the data. Components are sorted by the amount of variance they explain, in descending order. A common threshold is to keep enough components to explain 80 to 95% of the total variance. Here's the Python code to determine the number of components. First, PCA is fitted to the scaled data. Then, the cumulative explained variance is calculated. Finally, the number of components needed to reach a 95% variance threshold is determined. Now let's talk about the advantages and limitations of using PCA. PCA preserves the global structure and variance of the data, ensuring that the main patterns are retained. It is computationally efficient for large datasets, making it a practical choice for many applications. PCA removes multicollinearity in regression problems, which simplifies the models and improves their stability. It also reduces noise by eliminating low-variance components, focusing on the most important information. PCA provides a clear measure of component importance through explained variance, making it easier to decide how many components to keep. However, PCA assumes linear relationships between features, which may not always hold true in complex datasets. It may not preserve the local structure of the data, potentially losing some finer details. The resulting principal components often lack interpretability, making it hard to understand what they represent. PCA is sensitive to feature scaling, requiring standardization to work effectively, and it is not ideal for highly nonlinear data structures. Let's move on to T-distributed stochastic neighbor embedding, or t-SNE. T-SNE is a dimensionality reduction technique, particularly well suited for visualizing high-dimensional datasets. Here's how it works. First, compute pairwise similarities between points in high-dimensional space using a Gaussian distribution. The formula here calculates the conditional probability, P sub j given I, which measures how similar point j is to point I, given the Gaussian distribution centered on point I. Second, symmetrize conditional probabilities to ensure that the relationship between points is mutual. This formula averages the conditional probabilities P sub j given I and P sub I given j, then normalizes by 2n, where n is the number of data points. Third, create a random initialization of points in low-dimensional space. This is the starting point for the optimization process. Fourth, compute similarities in low-dimensional space using the t-distribution. The formula here calculates q sub ij, which measures the similarity between points y sub I and y sub j in the low-dimensional space, using the t-distribution. Fifth, minimize KL divergence between distributions using gradient descent. The formula here represents the Kullback-Leibler divergence, which quantifies the difference between the probability distributions P and Q, guiding the optimization process to make the low-dimensional representation as similar as possible to the high-dimensional data. To effectively use t-SNE, it's important to understand its key parameters. Perplexity controls the balance between local and global structure in the data. It represents the effective number of neighbors each point considers, and typical values range from 5 to 50. Learning rate controls the step size in the gradient descent optimization. If it's too high, the results may be unstable, while if it's too low, convergence may be slow or get stuck in local minima. Number of iterations determines how long the optimization process runs. More iterations allow for better convergence, but increase computation time. Here's a Python implementation of t-SNE using scikit-learn. The code shows a basic implementation with parameters for the number of components, perplexity, learning rate, number of iterations, and a random state for reproducibility. Finally, the t-SNE transformation is applied to the data. Finally, let's discuss the advantages and limitations of t-SNE. T-SNE excels at preserving local structure and revealing clusters in high-dimensional data, making it easier to identify patterns. It creates visually appealing and interpretable visualizations, aiding in understanding complex datasets. t-SNE works well with nonlinear relationships in data, capturing intricate patterns that linear methods might miss. It handles the crowding problem effectively with the t-distribution, which prevents points from clumping together. However, t-SNE is computationally expensive for large datasets, with a complexity of O of n squared, making it slow for very large datasets. It is non-deterministic, meaning different runs can produce different results, so it is important to run it multiple times. Distances and global structure are not accurately preserved, so it's best for local relationships and cluster visualization. t-SNE is sensitive to hyperparameters, especially perplexity and learning rate, requiring careful tuning to achieve optimal results. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.